All right, so this is where we had left off on Tuesday, whereby what we're doing now is we're deriving the equations of motion for a rigid body when in a rotating frame of reference. So this and a rotating and a translating frame of reference. And in order to do that, we have to define our rotating and translating frame of reference, which was lowercase xyz. And then you have your fixed frame of reference, in reference to which you have to find out everything, because those are the unit vectors that are not moving, right? And the thing to remember was that in the moving frame of reference, lowercase I hat, j hat, and k hat, well, k hat is constant because we're looking at planar motion. But in theory, in general, for 3D motion, lowercase unit vectors are not constant because you have rotation that's happening. And whenever you have rotation that's happening, the direction of the unit vectors is changing. So you cannot assume them to be constant. So where we had left off was that we were describing the velocity of point B relative to O in the moving frame of reference. And we were trying to find out what the velocity was. And we had said that this rate of change of x with respect to time in the I hat direction plus the rate of change of y with respect to time in the j hat direction, that's just going to be the relative velocity of B with respect to O. So we're good with that one. But now we have di over dt and dj over dt, lowercase I and lowercase j, which we need to find out how they're changing and how they're rotating with respect to time, right? So that's the mathematical juggling that we're doing right now. So I close my notes down. Give me 1 second, guys. Notes. This one. Oh, also, I posted the video for looking at geometry for solving one of the problems from last week. I hope you guys saw that. That's super important for getting potentially missing equations in your problems if you don't have them, right? So make sure you see that. Also, it's a really cool video because I'm behind like a glass screen and using like fluorescent markers and things like that. So
yeah, where did you do that video?
That was in the digital immersion lab at the Maker Innovation Studio in Portland. But unfortunately, can't do it live. There's no mechanism to do that lecture live. So yeah, it can only be recorded. Yeah. Yeah, unfortunate. Yeah, I have hopes and dreams of recording all the dynamics lectures in that medium over the summer, but that was a hope and dream from last summer and it didn't happen. So let's see how it goes this year. Anyways, also, have to convert everything from Mathematica to Python. Let's see how that goes this year too. Anyways, all right, let's go. So what we had said was that di over dt from calculus can be written as di over d theta times d theta over dt, right? And then this d theta over dt is nothing but the angular velocity, the angular speed rather, with which your frame of reference is rotating, right? So the next order of business is to find out what this di over d theta term is. And the way to do that is to express little I hat in terms of big I hat and big J hat, because we know that big I hat and big J hat are not changing. So that makes finding out di over d theta easily. Right? So what we do is we can write that little I hat. So what we're basically doing is this little I hat vector, we're going to write it in terms of the vectors capital I hat and capital J hat, right? So for little I hat, in terms of this angle theta, what is the component in the uppercase I hat direction? Remember, this is the unit vector circle, right? This is the unit circle. So the length of this little I hat is how much? It's just one, right? It's 1 unit. So knowing that that length is 1 unit and this angle is theta, what is the component in the big I hat direction?
Is it just cosine theta?
Absolutely. So it's just going to be cosine theta in the big I hat direction, and similarly in the big J hat direction, it's going to be, right? And it's in it's in the positive capital I hat direction, and it's in the positive uppercase. I use capital. Capital is the British way of saying uppercase, right? So you use uppercase I hat, it's positive, and the uppercase j hat, it's positive. All right, so we're good there. Now for little j hat, what we have to do is that we have to find out the components of this guy here, right? So to find out the components of this guy, right? So this is your little j hat, right? So this angle is equal to theta. That angle is equal to 90 minus theta. That's 90. So this angle is going to be equal to theta. So you're basically trying to find out what this component is and then what that component is, right? So what is the component of little j hat in the capital, in the big I hat direction?
Sine theta.
Nope, minus sine theta, right? Because you're going in the negative I hat direction. So almost there. So it's minus sine theta I hat plus, what's the component in the j hat direction? Capital J hat direction? Cosine theta. All right. So now, because I know that capital I hat and capital J hat do not change with time, right? It's the fixed frame of reference. I can just find out I can simply find out di over d theta by just taking the derivative of this, and I don't have to worry about I hat and J hat because they're constants, right? So the derivative of cosine theta with respect to theta, calculus people, minus sine theta, right? So minus sine theta uppercase I hat plus the derivative of sine theta with respect to theta?
Cosine theta.
Cosine theta. There we go. So cosine theta, capital J hat, like that, right? Now, what is this equal to? Look at these expressions, all three. What is this expression equal to?
Little j.
It's just little j. Di over d theta is equal to little j. Similarly, d little j over d theta turns out to be equal to, all right, so minus sine theta is minus cosine theta I hat, and then plus cosine theta becomes minus sine theta j hat. And what is this equal to?
Negative little I.
Negative little I. That's it. So you basically figured out everything that you need to figure out. So this expression here, equation number 1. All right, I might have moved too quickly. Let me know if you guys are good to move on to the next page. Good. All right. So
Good.
this expression 1, come on. So equation 1 becomes, right, you get the derivative of r of b with respect to o as a function of time is just equal to dx over dt times I hat plus dy over dt times j hat. And this is little I hat and little j hat plus omega times xj hat minus yi hat. I've just put in the terms for di over d theta and dj over d theta over here. All right, let's call this equation number 2. All right. This term here is just equal to VB minus VO in your absolute frame of reference, right? This expression here is just the velocity of B with respect to O. And this expression here is just equal to your omega crossed with x little I plus y little j, which is just omega crossed with r of b relative to O.
Yeah, why is it in the top equation? Why is it x in the j hat then y in the I hat?
Because we are rewriting this expression over here.
Wait, oh yeah, okay.
So
Yeah,
you basically, that x di over dt and y dj over dt, we found out what they're going to be equal to, right? So the one thing that I didn't write out was dj over dt is also going to equal dj over d theta times d theta over dt, like that, right? It's the same thing. So that's the expression that you get. All right, so I write this out. I see I have the expression that VB minus VO is equal to the velocity of B with respect to O plus the rotation aspect of things. Right? This expression should make a lot of sense to you guys, right? Because VB minus VO equal to V of B relative to O, we get for translation. And then you have a rotation aspect that's coming into the picture for a rigid body motion. All right? Makes a lot of intuitive sense. All right, so for any point, any 2 points on a rigid body, whereby you can choose a frame of reference at any one of those 2 points, this is the equation to end all equations for velocity, right? So velocity of B is equal to whatever the translatory velocity of wherever you choose your origin for your frame of reference to be, plus the velocity of B with respect to that point, plus your rotation aspect. Basically, now, previously what we'd seen was just pure rotation. Now we're combining rotation and translation, whereby you can have the motion of one point relative to the other. So this describes any possible motion for a rigid body, for its velocity, right? So this is called the velocity with respect to a moving and rotating frame. All right, very important equation. And also valid for any 2 points on a rigid body. All right, same logic applies. Okay, what are we going to do next? Predictions. We're going to find the accelerations, right? So we will differentiate with respect to time. And this is where stuff gets really, really interesting. You start getting a lot of things that are going on. All right, so differentiating this expression with respect to time, you find that VB dot is just going to be the acceleration of B, right? That's going to equal VO dot plus V of B relative to O dot plus the differentiation with respect to time of omega crossed with R of B relative to O. All right, so let's break it down. So this, let's call that part A. Man, using numbers and letters, you run out of things. Let's call this part, can't use I, we're using I as well. You know what? You guys are engineering adults. I'm just gonna do it what's easy. This is 1. This is 2. Let's say that is 3. All right, so let's break it down. So for the first one, right, that's easy. VO dot is just the rate of change of the point, the velocity of the point O. So that's just going to be equal to the acceleration of the point O. So that's what it is. Can't do anything with that one. All right, next we have the derivative of B with respect to O changing with time, right? So we have to break this one down. So d by dt of V of B relative to O. Right, and this V of B relative to O is just this expression that you see over here. Well, it's not that expression. It's just the rate of change of this expression here, right? With respect to time, because this is V of B relative to O. So that is just equal to derivation with respect to time of dx over dt little I hat plus dy over dt little j hat. Right, and you've got to do the same thing that you did in this term over here, but now it's just double derivative terms. All right, so I'm just going to write it out for you guys. So this is equal to, the product rule applies, right? So it's going to be d squared x over dt squared times I hat plus. You know what? I'm skipping a step, so don't mind me. I'm going to write the first term from here first, right? Because it just makes for simplified writing. Then I have the second term from here, which is going to be dx over dt times d little I over dt plus dy over dt times dj over dt. All right, are you guys with me? So now, oh, you good?
Is that d2i over dt? Is that dt squared in the denominator?
That's right. Thanks. Now, this term here is nothing but the acceleration of b with respect to O, right? It's just the rate of change of those points with respect to time twice, right? So that's the absolute acceleration of b with respect to O. This term here, you can do the same process that you did previously for your velocity, and the expression that you end up with, I'm not going to do it for you because you guys will have to trust me. You're going to get omega times dx over dt j hat minus dy over dt I hat. All right, it's this exact same process that we did to find out these terms over here, right? You're basically just finding out what di over dt is and dj over dt is. It's the exact same thing, and instead of x and y, you now have dx over dt and dy over dt. That's it. So you can just simply just plug that in there. All right. So this expression, similar to what we did earlier, so this expression is just equal to your angular velocity vector crossed with your relative velocity vector. All right, good. If I ever go to the next page and you guys have not done writing, just shout at me. It's okay. All right. All right. The third expression that we're trying to find is d by dt of omega crossed with r of b relative to O. Now, in calculus, product rule applies to two things that are multiplied. In vector algebra, I hope you guys learned this in linear algebra and differential equations, or you're learning this right now. For the cross product, it works exactly like the product rule. All right. So this is basically going to equal the time derivative of omega crossed with r of b relative to O plus omega crossed with the time derivative of r of b relative to O, like that. Right? And this term, that's just the angular acceleration of your rotating frame of reference. All right? So we can't do anything about that one. This term here, we've already found out what this is equal to, right? From this expression number 1 over here that we'd found out, right? So from that expression, what you end up getting is omega dot, which is, some people call it alpha as well, right? That's your first term. Plus, you get omega crossed with the velocity of B relative to O. That's just, I'm just writing out what R of BO dot is, right? So you just get V of B relative to O plus omega crossed with R of B relative to O. All right, adding it all up, you end up getting the expression that the acceleration of point B is equal to the acceleration of point O plus, you get 2 of these terms, omega crossed with V of B relative to O, right? Because there's one term here and there's one term here. So you end up with 2 omega crossed with V of B relative to O. Plus triple product, omega crossed with R of B relative to O. Plus, not done yet, omega dot crossed with R of B relative to O. Plus the acceleration of point B with respect to O. Another, the acceleration equation to end all acceleration equations. These two expressions, guys, basically the crux of dynamics that you need to know going forward for all of your courses that are coming up. All right. All right. So just become very comfortable with them. Let's break it down. Acceleration of point O is just the translatory acceleration with which your rotating and translating frame of reference is moving. Pretty straightforward. Omega crossed with R of B relative to O. We've seen this one before as well. This is just the centrifugal, centripetal, whatever, physicist. That's that term. All right. Angular acceleration, again, this is the intuitive term, right? So this is the angular acceleration term that you get. So angular acceleration, giving you a translatory acceleration component. Also easy peasy. Then you also might have the fact that your one point is accelerating relative to the other. That's where this term comes in. Okay. This term over here. Does anyone want to guess what this term is? You guys should have at least seen the theory in physics, one of your physics courses.
Is that gonna be tangential?
No, this one's tangential.
Oh yeah.
I love awkward silences. It's my favorite part. I'm going to give you guys 2 minutes because you should have heard about this before. In rotating, think about rotating of the Earth, crosswinds, things like that. Come on, guys. Have you guys heard of the Coriolis effect?
I haven't.
Oh, you should
Is
have
that
heard of
like, is that why like toilets flush in the opposite direction in like different
All right,
parts
that's a
of
big
the-
myth. Toilets do not flush in the opposite direction, but yes, it's that thinking. Why you have cyclones only going in one direction in the northern hemisphere, and they only go in one direction in the southern hemisphere. It's the Coriolis effect. So I'm
Isn't
going
it
to post
also like naval cannons across the equator?
exactly. Yeah. So I'm going to post a bunch of videos for you guys in the chat window. It's a really fun thing. So, Mr. Higgins, the toilet flushing one is the second video. So we can have fun with that. All right. So this, guys, I'm a math guy. I'm not like a physical guy, right? So this, I've now given you guys now know the from a mathematical perspective, from a dynamics perspective, where the Coriolis effect is coming in from for rotating bodies. All right, math is an absolute truth, does not lie. All right, you guys have questions? If not, let's move on to looking at a couple of problems. Three videos, all right. Okay.